All right, so I want to talk about momentum and impulse here, the introductory lecture. I guess a couple things to just remember off the top here. P equals mv. This says momentum is equal to mass times velocity. Velocity is a vector, and therefore P, or momentum, is a vector too. We can also say that impulse, see if I have room, is equal to F times T, because force is a vector, J is a vector too. We're going to talk about the difference between average force and maximum force. This is usually going to be F average, but we'll talk about there. I usually won't write that unless we're looking at graphs. Because we're looking at graphs here, this should remind us that what we have here is area equals base times height, which is pretty much the same formula that we have here, right? So this is going to be our area is going to be impulse, and it's going to be equal to the height, which will be F average, and the base, which will be time. So really, we're going to, in this next example, we'll end up using area to get impulse. And so anytime you see a graph like the one below, where you see time on the x-axis and force on the y-axis, you should be thinking impulse, you should be thinking area. All right, anything else I want to mention? Yeah, this is kind of important, and sometimes kids forget this. Impulse points in the same direction as the force. I think this is super important to remember, that the impulse points and it points the way the force points. And because in momentum we deal with collisions a lot between two objects, usually when we deal with impulse, we are only calculating the impulse for one object. Now we can focus on either object. Say if I threw a tennis ball at a wall, we could think about the impulse on the tennis ball or the impulse on the wall, but you can calculate it for, usually you just calculate it for one object at a time. Whereas our other momentum formulas, we like conservation momentum, we focus on the momentum of both objects. Okay, example 9.1. A rubber ball bounces off the floor and experiences the force shown in the graph below. So the ball is going to undergo an impulse. So maybe we have something like this. The ball is heading towards the ground, and then all of a sudden it hits the floor. There's an impact, and the ball is going to rise upwards like that. And so there we go. All right, I guess I'm getting Twitter notifications while, oh boy. All right, anyways, let's stay focused here. What is the impulse on the ball? So we want to know the area here. Obviously, the base being 8 milliseconds is a problem. So I'm going to go ahead and flip that. 8 milliseconds is the same as 0.008 seconds. And so just to clear that up, notice here that the force that the ball undergoes is at a peak right here at 300 newtons. So this is the force max that the ball experiences, and this is pretty normal, right? That the collision would not, the object wouldn't experience the same force the entire time, right? As the ball starts to decompress and then or compress and then decompress, and that you see a changing force value. So that's what we have with this curve, right? This triangular curve is a force that is changing over time. All right. So anyways, let's see. All right, try not to mess that graph up too much. So what we see here, though, with our area, hopefully, is a shape that we recognize, right? And that's a triangle. So if we just use the area of a triangle, we should be able to find the impulse here, right? So we're saying that J is equal to 1/2 the base, which is time, times F max. So while we normally know that J is equal to F times T, right? In this case, it's going to look a little different just because we're dealing with F max, not F average. And that's why the formula has the 1/2 in it, right? And that reflects the area of the triangle. So I'm going to go ahead and plug in my values. We want to know J. We know the time is 0.008 seconds. And we know the F max is 300 newtons. All right, so we just do the math there. And I think we're going to find that J is equal to 1.2 Newton seconds. We also can report that in terms of momentum. And so we could have our units of momentum, which is seen usually as kilogram meters per second. Reason being for that is that J impulse is also equal to delta P. So anyways, all right, so we got an answer there for our impulse. All right, what is the average force on the ball? Okay, so if we go back up and look at the diagram here, let's get a different color. We know that over this time period, there's a value of a force. Whoops, that was supposed to be dotted. Oh well. There's a value right here of some average force that could have accomplished the same thing. So I'm saying that this purple rectangle could have had the same area, or has the same area as the yellow triangle. And it would accomplish that over the same period of time with a different force, which is the average force. Why is it average? Because this force doesn't change, right, over that time period. And we want to know what that average force is on the ball. So now, since we're looking at the shape of a rectangle, we know for a rectangle, area is just equal to base times height, right, without the 1/2. As like we did for the triangle, right, up there. And so we can go ahead and say then that this time J is equal to F average times T, and it's the same T value. So I'm going to go ahead and just rearrange really quick because I want to know average force this time. And we can say F average is equal to 1.2 Newton seconds per 0.008 seconds. Cancel off those seconds. Don't need those there. And we're left with F average equal to, oh, I can't do that in my head. What is it? 150 newtons. So we see that the average force compared to the max force is half. Which I guess isn't surprising based on the formula of 1/2 base times height then base times height. But yeah, all right. So anyways, good deal. Let's go to the next page here. So this whole idea of momentum and in force, it feels like we're getting some new equations with J equals F times T, right? And P equals MV. And are we really though, right? And so what I like to do here is bring it back to Newton's second law, which everyone should remember is F equals ma. And we know from Newton's second law that A equals F over m. Then we should also remember that acceleration is delta V over delta T. And the reason I bring this up is if we cross multiply here, right? Just multiply these two and these two. We'll get something that looks maybe a little more familiar. Aha, right? And because we should know that change in momentum, delta P, is equal to m times delta V. And change in momentum is also equal to J. So what we have here is another way of writing, if I write over here, J is equal, because F times T is J is equal to m times delta V, which is delta P. So I guess I could have wrote that. Let me write it this way instead. And that's what we used there a second ago, I believe. Well, we use J equals F times T, but J is impulse, right? And or change in momentum, and that's kind of the idea here, right? Let's go one more step here, and let me see if I can also make this analogy. All right, so if I multiply both sides by, or divide both sides by delta T, I now have that expression, right, for F. And I can then say, right, I'll rewrite it one more time because this is getting kind of crazy over here. We can also sub in that delta P on top. And if this was calculus, you might recognize as F equals dP over dt. So the derivative of the momentum function with respect to time is equal to force. And what else can we say there? That's about it. So this is actually how Newton's second law was actually first quoted, that force is a change in momentum over a change in time, right? So, or the derivative of the momentum with respect to time. So this is how Newton's second law was originally coined by Newton. And but you can see that from F equals ma, right, which is what we think of as Newton's second law normally, we get this expression right here, which shows us that J, which is F times T, right? This is really just J, is also equal to m delta V. And so I just want to point these things out because it's going to be important in the next example. So what we have from this is the impulse momentum theorem, which is that the change in momentum is equal to the impulse. So kind of running out of room here. I don't want to write. I have any more room up here? Not really. But the idea is this. Let me see if I can go purple. All right. This is the impulse momentum. That's a hyphen theorem. All right, so, and you can see it right here, right? That the impulse momentum theorem is that J is equal to the change in momentum. And so there's a couple ways to write it, right? But if I just thought of, if you asked me the one way I would write the impulse theorem off the top of my head, it would be this one right here, m delta V equals F times delta t. But it's also correctly, whoa, that's not cool. It's also correctly stated, as delta p is equal to J as the impulse momentum theorem as well. Okay, now that I made a mess of the next page, let's try this example here if I can read it clearly. All right, so it says a ball of mass 0.25 is rolling to the right at 1.3 meters per second. And something really nice about momentum impulse is the before and after drawing. This just makes it super simple, and it makes these calculations pretty fun. I know students like these better because of the before and after. So we have a before drawing with a ball that's rolling at a wall. Velocity initial is equal to 1.3 meters per second. It's super important that you get the right sign here. And since it's rolling to the right, we know this is a positive sign, right? Okay. And then it's going to collide with, and it has a mass of m equal to 0.25 kilograms. All right, then it's going to collide with the wall and bounce back and travel backwards. Let's see, this way, left. And so it's super important also that you set up which way is which direction-wise, right? So here, I'm just going to draw this red arrow right here, up here, or double arrow, and call left negative and right positive, which is normally what we do, but it's nice to say that. So that's where I'm just deciding that that's the case, right? So VF is equal to, 1.1? And this time it's going to be a negative sign on it because the ball is moving left. All right, still has the same mass, so I'm not going to rewrite it. But good, drawings are done. What is the change in the ball's momentum? So delta P, whoops, I'm on the black marker. Delta P is equal to MVF minus MVI. It's very similar to displacement just being XF minus XI, right? And so we have delta P being PF minus PI, right? And each P being MVF and MVI. Okay, so that's where I got that from. All right, so let's go ahead and plug in 0.25. And VF is negative 1.1. And let's subtract 0.25 again. But this time times VI, which is that positive 1.3. All right, so then we'll go ahead and simplify that, and I think it simplifies into negative 0.275 kg meters per second minus 0.325 kg meters per second. No simpler units for momentum just because the ugly like kg meters per second every time. And you just got to deal with it. All right, delta P is equal to negative, right? We're just going to add those two together. Two negatives make it a larger negative, negative 0.6 kg meters per second. And there's our answer right there. Okay, good. All right, let's go to the next problem here. And here we have a stop to think. So I would pause the video and give this a try. What it says is you have a cart that is 10 kilograms moving to the left at 2 meters per second, and then it's going to hit the wall and rebound at 1 meters per second to the right. So go ahead, and it says, what is the change in momentum? So go ahead and solve that by pausing, hopefully. All right, so now we'll go ahead and do it. So first of all, I'm going to assign signs, right? If it's going to the left, I'm going to call this direction negative, call this direction positive. This is obviously My before is my initial, so I'm just going to say if I want to know change in momentum, that's delta P, which is equal to PF minus PI, which is equal to MVF minus MVI. And that's equal to 10, right? kg times, I might be able to write units here. Final velocity is 1 meter per second. I just don't like to write units if I run out of room. And we're subtracting that from 10 kilograms again times negative 2 meters per second. And so what you can see is the signs are going to be really important and might be why you guessed wrong on the answer. 10 kilogram meters per second. And we're going to have minus a negative, so this is going to be plus, and it's going to equal 20 kilogram meters per second, which is going to total up to, oh, dang. It's going to total up to answer F, which is 30. Whoops. I don't know what I'm doing. All right, isn't it answer F? Okay. So what we're seeing there, or why that's the case, is you have a cart that's traveling left, right, at negative 20 units of momentum, and it ends at positive 10 units of momentum. So if you just thought of it, right, like a number line, 0 in the middle, right, and it starts here at negative 20. And this is just momentum units, and it ends at positive 10. It starts to make sense now why the momentum, or the change in it, right, is positive 30. Because you're going from negative 20 to positive 10, right? You're going from 20 to the left to 10 to the right. So the impulse, or the change in momentum, is 30 to the right. The wall puts a positive force directed to the right on the cart, right? There's a force on the cart that's pointed this way. So our impulse also points this way. Okay, good deal. Let's go to the next one. It says a 150-gram baseball is thrown with a speed of 20 meters per second. It's hit straight back to the pitcher at a speed of 40 meters per second. The impulsive force of the bat on the ball has the shape shown in the graph below. Okay, so to start with, let's have the ball being pitched. Let's see, how can I draw this? Try and draw a bat. And it's going to hit this ball. And the ball is thrown to the left. And this is going to be all about the ball and not the bat. And that's important to understand, right? Because we like to do impulse calculations for one object, even though we can pick what that object is. The initial mass of the ball is equal to 0.15 kilograms. Then the ball undergoes an impulse, right, in the positive direction. Notice we have positive area, so that's why I wanted to have the ball being pitched left and then hit right, because we have a positive area up there because the line is above the x-axis. And so I'm trying to say that this area is positive right here, right, because it's above the x-axis. All right. Okay, so anyhow, final drawing, bat is still moving forward somehow, and the ball is now sailing in the other direction, and the final velocity is now positive, which is equal to, I'm going to do a positive sign, 40 meters per second. All right. Okay, so then it says, what is the max force that the bat exerts on the ball? So F max, we see from the graph up here, is the height of this triangle, right? So we can go ahead and say that if we know the impulse, we know the area, and we already know the time, we should probably get that time out of milliseconds. So I have 0.60 milliseconds, and I have to get to seconds. So my decimal has to move 3 times to the to the left. So we're going to go 1, because it's got seconds as a larger unit, and so our number has to get smaller. 2, 1. It's trying here. 2, 3. Okay, and that's it. All right, so we're gonna move 3 times, and we need valleys and all, or zeros in those valleys, right? So we end up putting 3 zeros on, and so we're gonna end up with 0.0006 seconds. All right, so that's gonna be the base of our triangle. So once again, impulse, right, which is J, is equal to area of an F versus T graph, right? This is time on the x-axis in milliseconds. Okay, so we can go ahead and say then J is equal to 1/2 base times height. We can say that J is equal to is equal to 1/2 F max times T. And we can go ahead and plug in some numbers, or we could rearrange this. I'm just going to plug in numbers because I think it's simpler to look at. But I don't know J, right? And I don't know F max. So this is a problem. So I think we got to get J first before we do anything else. So how to get J? Well, I'm kind of running out of room here, as always. Let's go ahead and just see if I have room. J equals delta P, right? And this equals MVF minus MVI, which is equal to 0.15 times VF, which is 40, minus 0.15 times the initial, which is, what was it, negative 20? It's for the ball. So we're going to, once again, end with adding here, right? Because we have a minus and negative. So we're going to end up getting 6 kilogram meters per second plus 3 kilogram meters per second. And then from there, that's going to be our J. We can then sub that. All right, this can then sub up to right there, right? And we can do this calculation. So let's go ahead and do that. So we're saying then room is just terrible here. I'm going to move down here for a little extra room. So we're saying that 9 is equal to 1/2 F max, which is what we want to know, times that time, which was that 0.0006 seconds. Okay, so then we can just multiply both sides by 2. Get rid of that half, right? And divide by 0.0006. And we get an F max. Whoops, I'm going to go over. I'm going to stay on this side. F max then is equal to 30,000 newtons. All right. And then part B says, what's the average force? So if we go look back up at the graph, we remember from last time that there's some average force over the 0.6 milliseconds. And last time it was half. Maybe this time it's going to stay as half as well. So maybe 15,000 newtons. Let's go ahead and calculate it just to double check. So J is going to equal F average times T. And J is still going to be 9. It's hard to see. And we want to know F average over the same time period, that 0.0006 seconds. So we'll just divide both sides by 0.0006, and I think we end up seeing that, just as predicted, F average is equal to 15,000 newtons. Ugh. Okay, tried to squeeze that in there. Hopefully that's legible and you can read that. All right, stop to think 9.4 says a rubber ball and a clay ball are each thrown at a wall with equal speeds. The rubber ball bounces, the clay ball sticks. Which ball receives the greater impulse from the wall? So go ahead and pause it, give it a try, and then we'll talk about this. All right, so in this example, I think once again, it's easier if you mathematically maybe look at it if you can't see that the rubber ball ends up winning out here. I think it's probably best to draw a picture too. So you have a ball that's flying at a wall at initial velocity of we'll just call it negative 10 meters per second. I'm just going to make something up there. We'll then go ahead and say it's a 1 kilogram ball. I'm just going to change it because I can, right? I don't like the way that looks. You might say it's actually a 10 gram ball, but does it really matter? I don't think it does. And I think it makes my math easier if I call it a 1 kilogram ball. Otherwise, I'm using 0.01 kilograms, which is pretty obnoxious. All right, so let's go ahead and say for the rubber ball, we know impulse is equal to change in momentum. So we can just find J equal to, I can write it up here, J equals MVF minus MVI. And so we know for the rubber ball that we have an MVF minus MVI. And for the clay ball, we also have the same thing. All right. And the mass here is 1. I'm not going to write units because I'm running out of room. Final velocity is, we can just make something up. If it bounces off the wall, we can say that it's obviously going to be going right because it's heading left initially. So I'm just going to make up and say it's going a little less because it loses some energy, 5 meters per second. It's going to make something up. Then I'm subtracting it from the mass, once again, 1, minus the initial velocity, which is negative 10. All right, so what we see is we have 5 then, minus a negative, which is going to be plus, right? Because when we do the math there, that's going to be a positive. And so we get 5 plus 10, which is equal to, J is equal to 15 for the rubber ball. All right, for the clay ball, it's going to be J equals 1 times VF, which will be 0 because it doesn't bounce, minus 1 times VI, which is negative 10. So 1 times negative 10 is negative 10, and then minus negative 10 would be a positive 10. So we can say that here, 1 times 0 is 0. We have 0 plus 10. So obviously the ball that doesn't bounce has a J value that is less than the ball that bounces. All right, so the correct answer is the rubber ball receives the greater impulse because it bounces. Answer B. Okay, almost done here. Let's go ahead and go to the bottom here. It says a 100-gram ball, all right, is thrown straight downward onto a hard floor. So it strikes the floor with a speed of 11 meters per second. The graph below shows the force that the ball exerts on the force that the floor exerts on the ball. I'm just going to go ahead and draw this really quick. So we have a floor here. A ball is headed downwards at an initial velocity of -11. And this is the before. The mass is equal to 0.1 kilogram, because 100 grams is 0.1 kilograms. The after, the ball is going to bounce, right, and head upwards. And this final velocity after the collision is is what we want to know, right? I think that's one of the things they're going to ask us. It says it strikes the floor with the speed of 11. The graph shows the force that the floor exerts on the ball. Calculate the height. Okay, so we want to actually know the height of the ball that it travels. But I think to know that, we're gonna start with knowing this final velocity. That's going to be the trick here, or the way to unravel this problem. So other than that, I think we're good. So let's look at the graph, right? So because we don't have a way to deal with these weird shapes, right here is a shape where we got a graph that's represented by a curve. We probably need to know a function of the curve, so we understand what the curve is doing, and they don't give us functions because it's not calculus. So instead, we just have to estimate this is approximately a triangle, and to solve this problem. So it's not as perfect as if we knew the function, right, of force as a function of time. If we knew that, then we could solve it exactly, maybe with an integral or something like that, where we can get the area under a curved object exactly, or a curved graph. Okay, so time is obnoxious again. It's in milliseconds, so we want to flip that. 5 milliseconds is 0.005 seconds is our t. This is a F max, right? Not an average. So if that's the case, then we're going to be using our area formula again, because the area is equal to impulse, and specifically the area of a triangle when we're dealing with the force max. If it was a rectangle, we'd be dealing with the average force. Okay, but we know it doesn't stay at 800 newtons all 5 milliseconds. Okay, so first thing, we'll calculate this impulse, and I think the idea is that if we know the impulse, we can then say down here that J equals mvf minus mvi, and get the final velocity after the collision. All right, so let's go ahead and do that, and then we'll worry about the height of the ball. So coming back up here, we can say that J, I guess I have room right here, is equal to 1/2 800 newtons times 0.005 seconds, and then just put our answer down here. And so 400 times 0.005, I think that's going to be about, I think it's going to be 2. So we can then say that J equals 2 kilogram meters per second. So we have an upward impulse, which is what we'd expect from the ball, right, as it undergoes this force, upward force from the floor. Yeah, that makes sense, right? The ball is heading downwards, and then at contact, there's going to be this force from the floor that is going to happen over the small period of time, and gravity is still going to exert a force on the ball, but the force from the floor is going to be much larger. So we're not worried about the force of gravity. Is kind of how we need to think of it. I think it's called the impulse approximation theory, the idea that you can ignore gravity. You know, like for instance, while the bat was hitting the ball, we didn't worry about the effect of gravity exerting an impulse on the ball, right? So that's kind of the idea, and then that's explained in the Knight textbook a little bit. Anyways, let's come back up here and plug this number right into here now. And so we can go ahead and say 2 kg meters per second is equal to our, what's our mass? I already forgot. Dang. Oh, 0.1 kilograms. Times our VF, which we don't know, minus our mass again, 0.1 kilograms, times our initial velocity, which is that -11. All right, so we do a little math there. We get 2 kg meters per second equals 0.1 kg times VF minus, this would just be 1.1. Add the 1.1. Add it or subtract it? No, subtract it. I got to be careful with my signs here because, you know, once again, minus a negative, right? So we're going to, this is going to be an addition sign. And so I'm going to end up subtracting 1.1 from both sides. So I get 0.9 is equal to 0.1. Now we divide both sides by 0.1, and we end up getting 9 meters per second. Notice it's positive, and that's important because we would expect an upward final velocity for the ball after it collides with the floor. Okay, good. So now we can go ahead and fill that in. Now they want to know what is the final height. How high up in the air does this ball go, right? And so we can solve that using some kinematics when we don't know time, right? We want to know what delta y is equal to, but we don't know time. We know the acceleration. The floor is no longer accelerating the ball because it's no longer in contact, so acceleration is equal to -9.81. And I think we have enough right there. We just need a kinematics formula that doesn't involve time. So which one doesn't involve time? Do you remember? It's K3, right? VF squared equals VI squared plus 2A delta Y. All right, so from that we can go ahead and plug in our VF, which is, so this is tricky, right? Because we got to do like a switch here, right? Because on the way up, right, on this part, now the VI is equal to +9, right? Because the ball is going to fly upwards, and the VF is going to equal 0. All right, and so we know that, and we'll go ahead and plug those in down here. Obviously, that's just 0. We could pretend this is the AP test and just go -10 there. I think that's fine. Let's make that change. So we have minus 20 meters per second squared times delta y, 81. We'll add or subtract 81 from both sides, yeah. Or no, let's just kick the 20 over there. That'll make it positive, which is nicer to deal with. Divide both sides by 20. and 81 divided by 20, and our only unit left is meters. 81 divided by 20, I don't have it crunched yet. Let me type it in the calculator. Should be a little greater than 4, right? 20.25. All right. And notice the sign is positive once again, so it ends with a positive position because it is moving upwards. All right, that's it. So hopefully that made sense, and for an introductory momentum lecture.